this demonstration, we're going to practice working with two extremely useful network administration utilities. The first one is called ping, and the second one is called traceroute. Let's take a look at ping first. Now, ping is a very useful utility that you can use to test, first of all, the reachability of a host over an IP network, and also to measure the amount of time it takes for messages sent to that host to be returned back. We're going to practice working with ping on the network shown in this diagram. We're going to send our ping request from our WS7 workstation right here. We're first going to send it to another host on the same subnet right here, and then we're going to practice pinging hosts on different subnets. First of all, on the next hop over from where our network resides to this network, and then we'll practice sending pings all the way out onto the internet. Now we can do this by coming down here and selecting our run command and running the CMD command to open up a command window. Now if we do an IP config command here first, you can see that my IP address is 192.168.6.11 for my WS1 workstation, and my subnet mask is 255.255.255.0. So my subnet is 192.168.6.0. There is another host on the same subnet whose IP address is 192.168.6.1. That's this host right here. So I'm going to send a ping request, ICMP echo request packets, from my WS1 workstation here to this host down here, which is another Windows workstation. And you can see that the host responds. By seeing the response, I automatically know two things. Number one, I know that the host is up and responding to network requests, and I know that network communications between the sender and the target host are good. So on this system, you can see that we sent 4 ICMP echo request packets to 192.168.6.1, and we had 4 ICMP echo response packets received back from that host. This tells us the IP address of the host that sent the ICMP echo response packet, the size of the packet, and how long it took, the round trip time. And as you can see here, because these two hosts are on the same subnet, this host and this host, the round trip time is really short. It's less than 1 millisecond. Okay, so we have practiced using ping to ping a host on the same network segment. Now let's ping the default gateway for our network segment. And we're going to do this a little bit differently this time. In our previous ping command, we pinged by IP address. Well, you don't have to ping by IP address. Ping is quite capable of using name resolution via DNS. Therefore, you can use a host name or a fully qualified domain name to ping a particular host. Let's enter ping da1.mydom.com. That is the fully qualified domain name of the router for this network segment, this host right here. Let's see if it will respond. And it does. You can see that da1.mydom.com was resolved into an IP address of 192.168.6.2, and that 4 ICMP echo request packets were sent to this host with a round trip time of less than 1 millisecond for each packet. And again, that's because the interface on this side of the router is still on the same subnet as these two hosts. I wanted to point out the fact that pinging by domain name can be very useful, because if you can ping by IP address and get a response, but you try pinging by host name or domain name and you don't get a response, that tells you that your basic network connectivity is working, but your name resolution system is not working. That can provide a very useful troubleshooting tool. Alright, let's take things out a little farther. We're going to ping this time a host clear out here on the internet. So we're going to cross multiple routers with our ping request to a host out on the internet. Let's do ping www.testout.com. Alright, notice here that once again we pinged by host name, and notice that the host name was resolved into an IP address by our DNS server, and that 4 ICMP echo request packets were sent to the IP address, and that host responded with an ICMP echo response packet. The round trip time is quite a bit higher because this host now is out on the internet, and these ICMP echo request packets have to traverse multiple routers to get out on the internet to reach the host, and then that host has to respond back through the internet with their ICMP echo response packets, and it takes a little bit longer. When we pinged on the same subnet, our round trip time was less than a millisecond. It was really fast. However, when we pinged the host out on the internet, the round trip time was quite a bit higher. The ping request had to go out on the internet, traverse multiple routers to reach the destination host, and the ICMP echo response packets that host sent back, again, had to go through the internet, through multiple routers, to reach my originating workstation. And as you can see, the round trip time took from anywhere from 75 to 77 milliseconds, where pinging a host on the same subnet took less than 1 millisecond. Also notice over here that the TTL parameter for each of these ICMP echo request packets is much smaller than when we were pinging on the same subnet. Up here, the packets didn't have to cross any routers, so the TTL parameter of each of these packets was never decremented. However, down here, the TTL parameter for each of these packets was decremented by, let's see, 9. That means there are approximately 9 routers between the sending host and the destination host. The TTL value of each packet was decremented by 1 each time it passed one of these routers. And the summary down here provides us additional information. It tells us the number of packets sent, how many were received. You will run into situations where sometimes you'll send 4 and receive 2 responses or 3 responses or 1 response. And that indicates that you have some serious communication issues. Probably the basic infrastructure is working, but there's congestion or a misconfiguration somewhere that allows some of the packets to get through, but not all of them. I've had that happen before. So that's how ping works. With this in mind, we need to shift gears now and talk about another troubleshooting utility that is extremely useful called traceroute. So let's practice working with traceroute. We're going to use the same network that we were working with before when we were pinging, and we will trace the route through various routers. First of all, we'll trace the route to the default gateway, which is basically one hop, and then we'll practice tracing routes farther out to hosts out on the internet. To do this, we use the traceroute command, and we are using traceroute on Windows instead of Linux, so the command is traceRT. As you can see here, on Linux it's spelled fully out, traceroute, R-O-U-T-E. There's also one other important difference between traceroute on Windows and traceroute on Linux, and that is the fact that traceroute on Windows uses the ICMP protocol to perform the task we just talked about. Traceroute on Linux, however, does not use ICMP. Instead, it uses UDP packets to accomplish the same thing. It functions in the same way, just uses a different protocol, UDP instead of ICMP. Because we're dealing with Windows systems here, we're going to focus on the ICMP implementation of traceroute. So let's first trace the route to our default gateway, which really isn't all that difficult because it's just one hop away. Traceroute, ba1.mydom.com. And just as with ping, you can either traceroute via an IP address or using a domain name. And again, using a domain name is useful because it will help you verify whether or not name resolution is working correctly or not. And as you can see, there's not a whole lot of information to be seen. We resolved da1.mydom.com into an IP address of 192.168.6.2, which is on the same subnet as the workstation that is sending it. It reached this interface right here, and we have our response of one single route, right? There's only one router. There's one hop. The round trip time was less than a millisecond, and here's the information, and the trace is complete. Let's take this a little bit farther now, and let's trace the route to this router out here. Okay, we're going to go through the first router, and then we're going to go one more hop to the second router before we actually go out on the internet. This time, let's do it using an IP address. Traceroute 192.168.0.1. Alright, so we've got our response. Now we had an interesting thing happen right here. Notice that it's showing 3 hops from here to the interface right here, but it's not. It's actually 2 hops. And the reason we get 3 is because, for whatever reason, this second request timed out. It took too long for that ICMP time exceeded error message to return back. And so we might have a configuration issue there that we need to work with. Either the router itself is not responding in a timely manner, or there could have been network congestion that prevented that packet from arriving in a timely manner, and so on. Once the router did respond, notice that the round trip time was relatively fast. It was only 2 milliseconds. So my suspicion is that that router just didn't respond in a timely manner. I don't think there's an issue with network congestion. I think more than likely what happened is it just took a minute for that router to wake up and respond to the request. Okay? Now let's take it one step farther and let's trace the route to a host out on the internet. Trace route www.testout.com. There's our first hop. Okay, there's the route to www.test.com. And I actually figured out why we are getting this request timed out error on our second hop. It's not network congestion, it's not the router configuration. It's because by default, traceroute is resolving IP addresses into host names. And this router right here does not have a record in our DNS server. Okay? And so it's trying to resolve the host name and it can't. And so then it runs the request again just using the IP address, and then it works. And that's why we're getting the request timed out error. All these other hosts, starting here and going down here, do have records in either my local DNS server or on a DNS server on the internet, and therefore are able to be resolved. There is an option with the traceroute command to disable name resolution. I'm going to open up a second command window because I still want to look at our results here real quick, but I want to show you the option. If we do a traceroute /, you can see that the -D option tells traceroute to not resolve addresses to host names, and that would actually fix the problem that we were running into. With that in mind, notice that there are, as we discussed earlier with ping, 9 routers, 9 hops between my sending system here and my www.testout destination system out here on the internet. Now showing up as 10 again because we had this error record right here where we couldn't resolve the host name, and we had to do it again by IP address. But you can see here that we start with DA1, my first router right here, and then we go to 192.168.0.1, which is this router right here. Then we go to the ISP's router, provided by Quest, and then we go through several different Quest routers, and then we end up down here to rackspace.net, and then finally we arrive at the web server itself, which has an IP address of 98.129.173.225. So that's how you use ping and traceroute. In this demonstration, we first talked about how ping works using the ICMP protocol, and then we practiced using several ping commands, and then we looked at traceroute. We talked about the way traceroute manipulates the TTL value to determine the path that a packet takes from a sending host to a destination host, and then we practiced tracing the route to several different hosts, both on a local subnet and out on the internet.